Are you ready to explode your mind? Welcome to the future of creation.
Analog electrical signals flow through wires as continuous, varying currents. But to compute, we force that chaotic energy into rigid, discrete states. In standard logic families, we map a flat 0 volts to represent a logic low, or a binary 0. A full 5-volt signal represents a logic high, or a binary 1. In digital logic, we represent this physical contingency with a D-shaped schematic symbol and the formal Boolean expression x equals a dot b. To prove how this math works in reality, we will use a simulated lab bench. Here, we can map abstract Boolean equations directly to measurable voltage changes. We will start by constructing the most basic logic gates, see how engineers scale them into universal manufacturing standards, and finally combine them to build the exclusive comparison circuits required for actual arithmetic. To track these physical behaviors, we rely on a truth table. This is an essential mathematical matrix that predicts every possible combination of input voltages and their resulting logical output. Binding binary numbers to specific voltage levels is what makes a physical circuit capable of processing abstract information. Our foundation is the AND gate. Think of it as 2 electrical switches wired in series. Current can only flow to the output if both the first switch and the second switch are closed. In digital logic, we represent this physical contingency with a D-shaped schematic symbol and the formal Boolean expression x equals a dot b. This notebook shows how the voltage table maps the 0 and 5-volt inputs to the logic states in the truth table. Looking at the bottom row, the output reaches logic 1 only when a full 5 volts is applied to both inputs simultaneously. The OR gate provides a different structural path. It operates like 2 switches wired in parallel. If either the first switch or the second switch is active, the current finds a path to the output. We draw this using a curved shield schematic symbol, driven by the Boolean equation x equals a plus b. Together, AND and OR gates form the bedrock of combinational control. They allow engineers to encode required contingencies and alternate data pathways directly into the hardware. To build systems that react dynamically, we must reverse an incoming signal. This single input operation is called a NOT gate, or an inverter. Using resistor-transistor logic, we execute this by routing current through a transistor. When a high voltage hits the input, the transistor switches on and shunts the power directly to ground, driving the resulting output down to 0 volts. In circuit schematics, this inversion is always marked by a small negation bubble at the output of the symbol. Looking at this truth table, we can verify the math against the physical circuit. The Boolean expression x equals a bar predicts a perfectly reversed output column. When the physical input receives a 5-volt signal, the output is strictly inverted down to 0 volts. Reversing a signal is the mechanism that allows circuits to branch. It enables the hardware to execute a different action specifically when an input is low. We expand our toolkit by combining these basic functions. Attaching a NOT gate to the output of an AND gate creates a NAND gate. Its truth table is the exact inverse of standard AND logic. A NAND gate outputs 5 volts in almost every scenario. It only drops to 0 volts when all of its inputs are high. Similarly, routing an OR gate through an inverter produces a NOR gate. These composite gates possess a unique mathematical property called universality. You can build absolutely any logic circuit using entirely NAND gates or entirely NOR gates. Imagine designing a complex computer motherboard. Initially, the schematic requires a mixture of distinct AND, OR, and NOT components. But by applying universal logic, an engineer replaces all of them with a unified array of identical NAND gates that performs the exact same mathematical function. This reduces the distinct types of components required in the supply chain. Instead of sourcing, printing, and testing 3 different integrated circuits, a modern factory only needs to mass-produce 1. Relying on a single logic family also standardizes the propagation delay, the fraction of a second it takes for a signal to pass through the silicon, across the entire circuit. Universal gates bridge the gap between theoretical Boolean flexibility and the rigorous constraints of mass manufacturing and power dissipation. As computations scale up, we require dedicated hardware to evaluate system states. This leads to the exclusive OR, or XOR gate, a complex combination of basic gates built to solve strict inequality. The operational rule is strict. The output swings to a logic high strictly when the input terminals are held at different voltage levels. We denote this exclusive operation with a plus sign circled inside the mathematical expression, written formally as x equals a naught b plus naught a b. This lab document captures the gate's anti-coincidence behavior. The formal Boolean expression sits directly beneath the voltage table mapping. Notice the middle 2 rows. The output is only active when we apply contrasting input voltages, 0 volts on one pin and 5 volts on another. Conversely, we have the XNOR gate. This is the direct complement to the XOR function, marked on schematics by an inversion bubble and a circled dot symbol. Its operational rule is the exact opposite. The output goes to logic high only when all inputs match, operating as a dedicated equality detector. Engineers deploy EX NOR gates heavily in parity checking and system error detection circuits. It continuously compares bits of data transmitted across a computer bus, verifying that the arriving voltage levels perfectly match the data originally sent. Exclusive gates prevent engineers from having to manually build massive, slow, basic gate arrays just to compare two pieces of data. Because physical gates directly map to mathematical expressions, we can use algebra to shrink hardware footprints before we ever solder a wire. Take a look at this raw, unsimplified digital logic problem. The initial equation uses 3 variables and requires an extensive layout of physical gates. By following the mathematical factoring, redundant terms fall away, simplifying the operation down to just x equals a naught b naught. This mathematical reduction saves physical space, power, and money by eliminating the need for unnecessary ICs on a motherboard. We have transitioned from raw voltage to basic logic, scaled it with universal gates, and enabled comparison through exclusive gates. But in all of these circuits, the output dies the instant the switch is turned off. If a CPU needs to remember data to execute code, how can we wire these exact same memoryless gates so they loop back on themselves and hold a state?
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.